Okay, thank you guys for coming. Welcome to week 6 of reverse engineering. Richard, Henry, and me will be presenting. Let's get started. Firstly, some announcements. This Sunday, OGIS will be presenting DRM circumvention. This is very closely related to reverse engineering, so that'll be fun. Fall CTF solutions will be released soon. Trademarked, we're working on it. Everyone is busy with midterms. And the fuzzing team meeting will be after this, right at 8. So stick around after the meeting. We'll have the fuzzing meeting. Here's the meeting flag, NSA backdoor. This is because Ghidra is made by the NSA, the software we'll be using today. Yeah, I'll give you guys a second to put this in. Again, if you've never been to a meeting, go to the website, FA2023.com, and then there should be a challenge meeting flag. Yeah. And if you haven't already, say hi to your neighbor. You know, we're all here to make friends. Okay. All right, table of contents. Firstly, I'll be going over some administrative stuff. Then we'll talk about RE. Then we have 2 demos. I'll be demoing Ghidra, and then later we'll be demoing GDB. And if you did not come to our Rev setup meeting on Sunday, please get started downloading that. There's the link to the past meeting, Rev_setup23. You need to download Ghidra, which requires you to install Java. So while I'm talking, begin downloading. It is probably useful for the challenge. Definitely useful. Okay, here's the scoreboard. Congratulations to everyone up here. Some notable things. Akil up 8K points, up 2 places, and we have someone new on the leaderboard. So congrats to them. Yeah. And Helper. So congratulations, everyone. You made it to week 6 accounting. Just wanted to do a mention of like how the officer structure works. So we have a flipped leadership model, which means you get invited to be a helper. So just some things we're looking for is that you're just demonstrating an interest in the club. So you come up to us and be like, hey, I want to help run a meeting. I want to help make a challenge. I'm interested in doing many things for the club. That's great. We'd love to have you help. Yeah. So talk to an admin or send us a message on Discord, just letting us know you want to help. Cool. Okay, recap from Richard's meeting. Reverse engineering. Reverse engineering is figuring out how a program works, usually without the source code. At Richard's meeting, he provided the source code. In these meetings, we will not have access to the original source code. Typically, you want to figure out the original intention of the programmer. And there's 2 major, not really exclusive techniques to do this. Static analysis. So this means looking at the code and trying to sort of just, see what it does. And dynamic analysis, this means you are running the code, and usually you're stopping halfway through the code or partially through the code and inspecting the state of the program. Today we'll be talking about C and C++ on Linux. These are called ELF binaries, executable in linker format. Later in the semester, maybe next semester, we'll cover Java reverse engineering and other types of reverse engineering, which include like side channels, virtual machines, and symbolic execution. Compilation. Most of you guys hopefully have taken, or maybe not everyone, but your source code gets converted into assembly or machine code by a compiler. So you may have heard of Clang or GCC. So this takes the code you wrote and turns it into a format that the computer can read. This process is not reversible. So once it's converted into an executable, you can't really ever turn it back into the original source code, only the best guess of what it's going to look like. Also assembly. So this is what it gets transferred into. Sam ran a meeting on this recently. Yeah, assembly is just abstraction over the machine code, right? So every single program you write will eventually be transformed into this format, which is sort of just like a very simplified programming language. So there's a bunch of general purpose variables called registers, and you get to do like sort of limited subset of commands with it. So you can add registers, you can subtract, you can dereference them, stuff like that. So here's an example of what this process might look like. On the left, I have the C code, and on the right, you can see how it roughly lines up to the assembly code. And there's also some basic CPU structures for this, notably instruction memory. This is all the code for your program. Registers, these are these variables I talked about earlier in the stack. So anything that requires more memory, or maybe local variables in your program will go on the stack. And the registers are just used by the CPU to kind of shuffle around where these variables are. There's also the heap and like global data segment, but out of the scope for this. Okay, now I'll talk about compilation, decompilation. Okay, so you guys can go on this website, godbolt.org, and you can put in any snippet of C code you want, and it will output what the assembly for this program looks like. So usually it's pretty easy to go from C code to assembly. Now I have a challenge for you guys. Can you go from assembly to C code? Raise your hand. Do you know what it does? I'll give you guys a couple seconds. Yeah, it's pretty hard. This is a very hard process. This is why we have tools like Ghidra. It's really hard to go back from assembly to C code. So now that you have the C code, it maybe makes a little more sense. But this process, which is called a decompiler, is the tool you'll use. We'll take the assembly and sort of convert it back into pseudo-C. So this isn't going to be a perfect conversion. It's going to be this program's best guess at what the original source code looks like. So just another term here, a disassembler will take the bits and turn it into assembly. Decompiler takes the assembly, converts it into sort of pseudo-C-like code. Another thing to note is that decompilation isn't always the same. So on the left, I have my original program, and on the right, I have the program that Ghidra thinks it looks like. So if you look, there's sort of like different control flow here, right? There's like a do-while loop instead of a for loop. Maybe there's an additional if check. So functionally, these programs are equivalent, but like the semantics. So like there's many ways to write the equivalent set of code. So Ghidra doesn't really know the exact way it was written by the programmer. Yeah, just one thing to mention. Okay, now I'm going to hand it off to Henry to talk about optimizations. Up here.
Oh. Okay, so as you can see, C compilers typically do a lot of optimizations in terms of your code when converting from your C code to the assembly code to make the processor run quicker. This is one of the example. As you can see, when loading an array with bytes, it loads the first 8 bytes first, and then loads, well, probably the next 8 bytes, and then the rest pretty much. So here, you can see that we have a string hello world, and it is really just a car array when I read it that way. But in there, it's actually split into 2 segments, and it's backwards. But you can see here, it is 8 bytes, and then the rest. And do any of you guys know why this backwards?
Stack goes down.
Kinda. Stack is one of the factors, but in x86, there's also this concept called, not x86, there's this concept called endianness. And in x86, the processor uses a design called small and little endianness. So it stores the least significant byte in the most significant position. So it is backwards by design. And also that you mentioned, yes, instructions do go backwards because it's designed in the stack, so everything is backwards. I don't know. Assembly is strange. And yes, I did just spend 3 hours this week debugging why memory like when I was trying to compare memories, why it doesn't work because it's backwards. Yes, I did learn something this week about this. And another optimization, this is probably like you saw this in EC120 if you took it. When you're trying to use modulo, For example, here mod 4, because it's like 0, 1 to 3, so it's really the last 2 bits of the number that you're trying to find. So actually, it will just do an and the last 2 bits. The rest will be discarded. So regardless of your implementation, actually, in this case, the compiler will always turn it into this case. So you don't have to worry about the efficiency, whatnot. And yeah, that's how it's being optimized. And as you can see, the pseudocode that Ghidra produces doesn't really know the type. Here is the u long, but it's really unsigned in. So anyway, that's for optimization.
Okay, thank you, Henry. Now I will be opening Ghidra. So if you have a Ghidra on your computer already, open that up and download Debugger is the challenge I'll be looking at today. So that should just be somewhere in there. Let me know now if you don't see it, but that's a challenge you want. Yeah. How many buttons on this? All right. I'm not sure of my ability to zoom in. I know Ghidra. It's like, oh no way, they actually added this. Huge. Okay, so let me start from a new project. Would be this window. Okay, so you're gonna pop into a window that looks like this, and then you're gonna hit a file, import file, and then download your challenge. So you notice that it already was able to determine this is an x86 binary, and it was compiled with GCC. It's little endian and 64 bytes. Bits, sorry. Oh boy. Okay, so once you open it in Ghidra, it's going to ask you to analyze the program. We're going to hit yes. And then there's a bunch of options. So these are typically you can leave them all on defaults unless you have a very specific use case. So I'm just going to hit analyze. And if you get that security warning pop up, that means you need to go to your system settings. This is usually just a Mac M1 thing. And allow anyway. And reanalyze. So I can hit this analysis, auto analyze, and hit analyze again. And hopefully there's no errors. Okay, cool. Now we're in Ghidra. So there's a lot of parts to Ghidra. So in the middle pane is the assembly of the program, which is pretty daunting to look at when you get started. On the left is sort of your overview of the program. And on the right, it's a decompiler. So if you notice, we haven't selected a function yet, so there's nothing up there. So I'm going to go into the pane called Symbol Tree, click on functions. And what function should I click on? Any guesses? Any suggestions? C program. Where should I start? Yeah. Yes, man. Okay, cool. All right, cool. So we see our program. Does anyone know the arguments to a C program? Yeah, like the format of the arguments. So if we notice Ghidra mistyped it. So it thinks our first argument is an int and our second argument is a long. So if you guys have done anything like C or C++, you should know this maybe isn't completely correct. Any suggestions? Yes.
But between int and a bar star array.
Yes.
Or rather,
Star. Work too. Double pointer to a character. Kind of, yeah. Yeah, what you said is correct. Okay, so we can click on variables and we're able to rename them. So you can right click and hit rename For the rest of this, I'm going to be using this hotkey L. It's a little shorter. So L, and we know this is going to be our argc. And then this is going to be our argv. And you notice the type is also incorrect. So I'm going to right click and you can hit a retype variable. Instead of long, we're going to do char double star. So the reason we're able to do this is we're just making some assumptions that this is a standard Linux program. And we also know the return value is going to be an int. We can do that as well. Okay, so let's take a look at what we have. So if we have less than 2 arguments, it's going to output this message. It's just going to say that we need to specify a second argument, right? We need to specify that one. And then it's going to get this length of our second argument, presumably the flag. So I'll just rename this to like flag length. Okay, now we see this big chunk of assignments starting at local 38. Does anyone know why it looks like these giant integers and maybe not like something else we've seen? Anyone raise your hand? Yes.
It looks a lot like that string conversion we saw that assembly.
Yes, exactly. So the program has our compiler has optimized this. So we know that this is probably, since it's 15 hex 15 long, or 21 characters long, we know this is probably a character array, size 21. So what I'm going to do is I'm going to retype this. So we're going to start at local 38. That's the first one we see. And I'm going to right click and I'm going to hit retype variable. And this is going to be char and it's going to be 21 long. Let's do byte. But char has like a minus value, probably not what we want. Okay. All right, cool. So now this looks a little more readable. And this is some like unknown thing we're comparing to. Okay. So then we loop over some counter. So I'll just name this I for convention. And we know that we take unknown I and we XOR it with our index. And then we mask it with 7. And then we subtract 8. Does anyone have an idea what the masking with 7, this and 7, what an equivalent operation could be? That was also in the slides earlier. Yes.
That's going to be a modulo operation.
Yeah, so this is equivalent to modulo 8, which makes sense. So maybe that means that this last bit, maybe this last chunk that we didn't type is 8 bytes long. So I'm going to do that right now. This is, I'll just call this like unknown 2. And we know the type is probably 8 bytes, right? Because we're indexing into this and it'll never be more than 8. So retype. Okay, cool. So it does some sort of operation on the unknown. And then it compares it to our input. So it's going to take this big long array, do this kind of complex calculation, and then compare it to whatever we provide to the program right here. And if that's correct, string compare will return 0 if the items are identical. So I'll just name this like is not equal. Yeah. So if they're equal, the flag is correct, otherwise it's incorrect. And then this is just our return value. And this is probably as far as we can get in Ghidra. It's probably going to be a pain to like understand at this point, like what this computation is doing and how to like solve it. So while it could be solved statically, a better technique might be to add a breakpoint into our program. So since we know it's just comparing this result at line like 50 to our input, why don't we try to set a breakpoint right before it compares it and see what it wants the value to be. And for that, I'll hand it over to Richard, who will explain how to do that. And before I hand it off, do you have any questions on what I did or want me to go back to a step? Oh, boy. Yeah.
What was the type that you were on variables?
Yeah, so I converted them all to byte arrays. So the first one I converted to was a byte of size 21. And the reason I did this is I made a guess, I made an assumption that the length of the array would be the same as our input flag length. Yeah, any more questions? Just so,
No, that was my question, is to remember exactly what you did to convert the.
yeah. And just as one more rename, I'm gonna rename unknown2 to our key. It's probably just some sort of better name for it. Okay,
Well, can you scroll back down to the bottom?
yes.
Um,
You wanna start?
all right, so now we're gonna run this in GDB and see what we can do with it. And we want to set a breakpoint like right before the string out, so we know what it's compared to.
Do you wanna put your computer there?
Are you in Zoom?
I am in Zoom, yeah. That's me.
Yeah, his name.
Yeah, you guys can see the screen. Excellent. So here we have.
Can you try zoom in?
I will zoom in the terminal. Boy, it's massive now. All right. This will fit like five. This will fit like 5 lines on here. Okay, so we've got our program. It's called debugger, and let's run it with GDB. So I have PwnDebug installed, which is a very helpful tool. You guys should install. If not, you can
slides for this, right? Before you start with them.
we have slides for this.
Like, oh, you mean on the.
The demo was all the way to the bottom.
It's
Yeah,
just like a
actually-
cheat sheet. I mean,
You can delete it.
There's the Ghidra cheat sheet when you download the slides. I won't go through it because it's just what I just did.
okay. So. Ghidra cheat sheet. Okay.
Yeah, if he does this, then he gets it done.
Okay.
Okay, I was gonna do it the other way around, you know, you can do this too. So what can we do in GDB? We can look at program state, we can analyze the variables, set breakpoints. All this is going to become more clear once I actually have GDB pulled up. So breakpoints are places in the program where you can stop at and see different parts of the program and how their current state, like their current values as you're running. The next slide, please. So yeah, GDB, that's sort of an old UI. We'll be using PwnDebug, which is a pretty different UI, which is on the next slide. If you don't have it already installed, go ahead and install it by doing a git clone. I think this should have been covered to rev setup, but if not, you can go ahead and do that. Pretty simple setup. If you already have GDB installed, just clone this repository and run the setup script. It's PwnDebug, PWNDBG. All right, so yeah, now we'll go on to the GDB follow along.
Can you make a note for M1 that I can't do?
Yes, M1, you can't do it. I'm sorry. There are issues with. Actually, M1 users can do it if they do like a full system emulation. Oh,
So too slow.
too slow. Pete says it's too slow. He's a fast guy. Okay, so let's jump ahead to the follow along. You guys can all see my screen here. Okay, anyone need this bigger? Everyone's here fine? Okay. Very good. So once we open GDB, it's gonna give you a bunch of this info. Most of it can be ignored. If you don't have PwnDebug installed, it might look a little less colorful. That's okay too. So let's see. The first thing we can do is we can run the program. So to do that, simply type run in this prompt that comes up, the PwnDebug prompt. We'll run the program and it says usage debugger flag. This is pretty clear from the reversing that it needs an argument. That's the first argument is the flag that's checking. So let's give it an argument. How do we do that? We can just simply do run and supply argument directly to it. So let me put in a bunch of numbers, right? So here there's 20 digits right here. We're going to run this again. And it says the flag is incorrect. Oh no. How is that the case? Well, because that's not the flag. Right. So sorry. So how do we figure out what the flag is? So from the reversing we've done through Ghidra, we see that it compares your input after some mangling to a constant value. So let's see what those values are. Now remember from the Ghidra view that we have to bypass the first if statement, which checks the flag length. We know that the flag length is 21. So let's supply 21 characters in here. And then now what we need to do is set a breakpoint. Right, so how do we set a breakpoint? First, we should do is disassemble the main function. This lets us know where we want to set the main, or where we want to set the breakpoint. So type dis, which is just shorthand for disassemble mains. So here we have a lot of assembly. It doesn't really, you don't really understand what all this does, but just understand that this is the code that is in the main function. Right, this is what Ghidra decompiled into the nice output we have in the Ghidra window. So here I can already see this stir and string compare. So this is the function that compares our flag with the input, or with the correct flag. So let's set a breakpoint. To set a breakpoint, simply do break, and then star. So the star here is going to indicate that you want an assembly address and not a line number. So this distinction is kind of important. Just always use the star if you're getting a breakpoint from the disassembly view, or getting a breakpoint address from the disassembly view. So what you can do is you can do break star main plus, and you can see the string uncomp is at 252. Right, that's the offset from main. So what this is going to do, once I hit enter here, is it's going to set a breakpoint at this stir and comp function. So before it runs this instruction and does the call, the program is going to stop here and let us look at the different registers and stack and variables in this. All right, so now let's run it again. If you just type run without any arguments, it will use the arguments from the last invocation. So before we ran it with 21 digits, so it should get to this point in the program. So let's run it, and let's go. Let's see. There's the flag. Pretty straightforward. It just compares the flag with what we've entered, which is the series of 1, 2, 3, 4s. So yeah, that's a primer on GDB. For this particular challenge, it was pretty simple, but I think for some other ones that we've had for you today, you're going to be a little bit more difficult than this. So any questions about GDB? Any part of this demo?
So it says strace or ltrace.
Use strace or ltrace. Oh, ltrace is actually applicable here. Wait, I don't have ltrace. Okay, well, that's for another day. Maybe round 3, we'll cover ltrace and strace. Yeah, that concludes the GDB demo. Thank you for paying attention to that, and let's wrap up the meeting now. So I'll pause here real quick. So this is a very good cheat sheet for the GDB commands. The GDB itself is a tool, and pwn_debug is another tool. So I've split the cheat sheet into commands that are specific to GDB and specific to pwn_debug. But if you've installed pwn_debug, you just use whichever. So these are, so the ones that I've used today are the first one, b main. So for a lot of these commands, you can just type the first character and it's the same as typing the whole thing. Instead of typing break, you can type B. Instead of typing run, you can type R. So yeah, I'll let you take a look at this at your own leisure. These slides are on the website. You can access them there. And then next we have the Pwn debug cheat sheet, which covers some instructions that are maybe more useful for Pwn. But they should also be helpful for doing the rep challenges. All right, so go try for yourself. Go to ctf.sigpwny.com. Start with Crackney 0. There's a whole series of Crackneys and some other challenges. Ask for help. Practice is the best way to learn. So go ahead and do it. Next meetings this Sunday, we've got DRM circumvention. Should be very exciting. Hope you guys will all be there. And next Thursday, we'll be talking about crypto. That's the cryptography crypto, not the cryptocurrency crypto. So excited for that too. Thank you guys all for coming today.
I haven't heard about like Boolean types.
I do actually.
One more thing, if you guys are, so the fuzzy meeting is going to be right after this at 8 p.m. So you guys can stick around for that if you're interested in fuzzing, or if you guys are already a part of that, please stick around. Yeah, it'll start at 8 p.m. Thank you. Appreciate the information. Yeah, raise your hand for questions, guys.
Oh my gosh. Raise your hand for questions, please. Thank you. We'll help you.